Yes, so yeah, welcome to the third talk today. It's a great pleasure for me to introduce Larry Paulson, one of the inventors or original implementers of the Isabelle theorem prover, which I'm happy to use, a happy user since over 20 years, I've counted. And with that, I'm handing over the floors to you.
Okay, thank you very much for that introduction. So today, as the title says, I would like to talk about some personal experiences which I've been doing and are continuing to do right now. So a dramatic thing happened over the new year when Joseph Urban announced that he had formalized like a whole book of topology. That somehow they'd got the book into LaTeX form. I think there's some PDF to LaTeX translator, and fed this LaTeX source to, I can't remember, I guess ChatGPT and Claude he used, and just told it to go and not stop until it was finished. And somehow they had produced this enormous amount of formalized material, and this is advanced material. So I'm not sure what Urison's lemon, the metrization theorem, and Tizzi extension theorem are, but I have seen their proofs, and their proofs are seriously non-trivial. And it is cool that you can just feed a mathematical text into a computer, wait a few weeks, and out it comes. Now, for some reason which I still no one quite understands, this experiment was first done using a thing called Megalodon, if that is how you pronounce it, by Chad Brown, which I think no one has heard of until now. And the thing is, it had a very small library, so I believe it had the real numbers, so at least that the AI did not have to construct the real numbers, but it had very little else. So this was really from a blank slate producing all these advanced theorems of topology. Now, people like myself complained, why didn't you use a proper theorem prover? And so he reran the experiment using Hall light, and then also he ran it in Isabelle Hall. So what he said, now there's a paper you'll find on arXiv in which he describes this, and if you're looking for the paper, you just search for 130K lines and you will find it. He says he had some kind of long-running feedback loop. I saw the prompt, it was about 2 pages long. It looked, to my mind, it looked like leaving a list for a teenager who you don't trust very well, who you're leaving in charge of the house for a couple of weeks. So do this, don't you dare do that, keep doing this, don't do that, for 2 pages. And somehow this is a kind of computer program, and it proved all this stuff. And it's amazing. So, but now I want to talk more about a different thing. They're related, they're both AI, which is the stuff done within AWS by 2 people I know there, that is Hanno Becker and Dom Milligan. What they've got here, first, the thing called IQ, which is a component of the tool set, which is, I don't even know what an MCP server is, but I guess it allows the agentic thing, your language model, to communicate with a running Isabelle session and cause it to prove things. And the issue, of course, especially Isabelle as compared with a simpler system like Hall light, is that Isabelle is designed with a user interface to be used by people. It's not intended to be used by an agent, and you need to put in a hook in a sensible way so that the agent can communicate with Isabelle and get back some kind of response that's intelligible to the agent, as opposed to being intelligent to a human user. So there is a big task to do there, which is done by IQ. And IR, and I actually am not entirely sure exactly what the differences between the two are, but this IR is in particular a read-eval print loop for Isabelle. For this, so this is my previous comments actually applied more to IR, I suspect. That is to say, the ability simply to send commands to Isabelle and get some kind of reply back from Isabelle that an agent can use to interactively explore a proof. These two have been combined with, if you like, an interface which allows you to do a whole bunch of things. Now, I've been using this for a couple of weeks now, and it's what I will mostly be talking about today. I'm afraid I only used the prompt box. So Isabelle Assistant comes with many particular features like explain the purpose of this code, convert this ugly code, like refactor it into a more beautiful form, suggest the next thing I should do. So many things of that sort, even give me a nice name for this theorem. And I haven't dug into the code, but I suspect every one of these, like these are buttons, and if you select one, it simply sends a prompt to the prompt box. And I've just been using the prompt box, and that's what we'll be looking at. And by the way, anyone can grab this. You will need an AWS account to power it, but the actual thing, the actual tool set is freely downloadable by anybody right here. Okay, so what did I do? My first experiments, so I had the source of that topology book that I mentioned earlier, and there was a theorem that was mentioned that I knew we didn't have in our library, so I thought, well, I want to grab this theorem. But instead of feeding in the whole book like they did, and I'll talk more about the problem later, but clearly if you feed in the whole book, you get 130K lines of God knows what, and how are you going to find the things that you want, things you don't want, how good is the code? All of that is kind of not really under your control. Whereas if you're doing it interactively, so you've got an open Isabelle session, just as if you were proving it yourself, but instead of doing the dirty work of typing actual proof tactics and writing your own proof, you talk to the prompt window instead and feed lines of LaTeX to it, 2 or 3 at a time, that are describing the next step of the proof. Then it writes the code for you. And that seems like a much more civilized way of doing it. And in a couple of hours, maybe 1 hour, I can't remember exactly, I had a proof of Urysohn's metrization theorem. It was entirely generated by machine, and it was really not a bad-looking proof. It was indented, it was structured, it had reasonable names. We'll see. I'll give evidence of this later. We're going to look at some proofs in detail. They really look quite decent. And maybe this made me too optimistic, because then I tried a different thing, this proof that the Ramsey number of 3 and 6 equals 18. Here I ran into a lot of headwinds. And there is a certain frustration in this kind of interaction, because the language, whatever, Claude, the language model that you're dealing with, takes its time, even with a very simple request. It thinks and thinks and thinks, and maybe 10 minutes later, maybe you'll do a huge amount of work. Maybe it'll give up, or maybe you'll see it going off what looks like a tangent. Maybe you want to kill it. So I got a long way with this proof. And then I could see it wasn't quite clear how to continue. It didn't quite follow the argument. I didn't quite follow the argument. And then I thought, do we really need a formal proof that R of 3, 6 equals 18? And by the way, someone else has formalized this, which is very annoying, but I gave up on that one. Incidentally, as an example of the kind of difficulties we face when formalizing mathematics, part of this particular proof, now I haven't explained what a Ramsey number is, and I hope that doesn't annoy anyone, but Ramsey's theorem is about graphs. And it is in particular saying that every graph of at least 18 vertices contains either a thing called a clique of size 3 or a thing called an anticlique of size 6. Now, part of the proof that it is 18 is proving that it must be greater than 17. And the way you do that is by exhibiting a particular graph of 17 vertices that doesn't have these cliques and anticliques that I mentioned. And how do you do that? Well, you actually have a picture of this graph with its 17 vertices, with its edges. And now, are we imagining a language model that's going to read the graph? Well, they can read diagrams. It can then identify the edges in the graph. How exactly is it going to find the cliques? I'm not sure. How long does it take? This is exponential algorithms, brute force search. I hadn't particularly thought. Now, if someone said, now you will do this by next week or else, then of course we would have to try. We would have to see if the a fairly basic proof could not merely check that there are no cliques, but prove that there are no cliques and so forth. That would be a task to do, but this is not what ordinary mathematics feels like. You know, when a normal mathematician would look at the graph, frankly, they'd probably say, I believe you, in fact. But if they didn't believe you, then they would look it over rather carefully for a while until they were convinced. But clearly that is not a formal proof. Of making a formal proof of a fact of this kind is the sort of tedious thing that makes people want to give up on formal proofs. So that was another experiment. What else did I do? Well, I was experimenting with a different way of doing group theory. And one of the cool things here is, and group theory is very well known, and Claude has absorbed a lot of group theory books. So, for example, at one point, I realized there were some basic properties of group theory that I'd completely overlooked. And suddenly it is of its own accord saying, right, I need a theory of a thing called the center of a group. So it defines the center of a group, and then there are various properties that are well-known properties of the center of a group, and it just goes ahead, formalizes them in Isabelle, and not just in Isabelle, but in Isabelle using the formalization of group theory I was playing with there, which is different from Isabelle's standard formalization of group theory. So somehow it reads the whole thing and says, somehow, aha, this is how he's formalizing the group primitives. Now I can formalize the center of a group using his primitives and prove all the theorems, and all without being told to at all, simply because it was needed for another reason. And that's pretty impressive. I also tried translating whole proofs from Lean and from Holite, which I will say a little more later. So here is one. So as you see in the diagram, Feuerbach's theorem is something to do with circles and triangles. I can never remember exactly what it is, and it is quite a complicated thing with a bunch of cases. Although the Holite proof that I was starting with, which I guess was due to John Harrison, was only a couple of hundred lines long. So what happened with Feuerbach's theorem? I struggled a bit. First of all, this proof uses the without loss of generality tactics. Now, what does that mean? So very often in mathematics, you've got a particular, let's say you're looking at a particular line, and they say, well, without loss of generality, one end of this line is at the origin. Okay, and then they say, well, without a loss of generality, the other end of the line is kind of at 1, like it's on the x-axis, and it is unit, this arbitrary line segment is suddenly a unit line segment lined up starting from the origin. That makes a proof a whole lot easier. Then you prove it that way. And the magic of these tactics is that they somehow map this simple proof to the general case. Now, Isabelle doesn't have much support for this sort of thing, and maybe that is one reason why the proof turned into such a monstrosity. As it says here on this sad slide, I did need to give a lot of hints to Claude here and there, and I even had to run Hall Light from time to time and say, oh yeah, this is where we got to. This is a thing you need to prove. Obviously, that's a big hint. And the proof blew up by a factor of 7, which is not very pretty. I have to say these auto-formalized proofs do tend to be very verbose, and we'll say again a little more about that later. I managed with a fair bit of effort to shorten the proof a bit, but it's still rather ugly. We should have a peek at the original material, though. So imagine giving this to a language model. I think it formalized this one automatically. Yeah, I think it formalized this theorem fully automatically. I should apologize, actually. What I should apologize for is this syntax, because although this is Hall Light, I'm to blame for this. This syntax already existed by about 1984. So please accept my apology. By the way, this is not the whole proof. This is not the whole proof. Can you read this, by the way? No one's reading this. And even this is not the whole proof, because even this, so that is a whole lemma, but it's only the first lemma. I'm not showing you the actual proof. So I just wanted to give you an idea what Hall Light looks like and to give the language model an excuse for not managing to prove the whole thing automatically. Though I did do this lemma, and it wouldn't surprise me if somehow it recognized the statement of the lemma, which is something about circles, and proved it its own way. That wouldn't surprise me. Now, I have more examples, but before I get into them, I wanted to comment a bit on what I saw just from this. It is impressive how natural looking the code comes. So obviously Claude is a general purpose model. I think it's probably more designed to produce C code than Isabelle. And yet the names it chooses seem reasonable. They seem very much in the spirit of other names used in other Isabelle formalizations. And there are some weird quirks of Hall Light that it does not copy. So one of the weirdest things in Hall Light is very often, instead of referring to type real, which is the real numbers, of course, it has the vector space R to the 1, which obviously is the same as the reals. But somehow when you write it as R to the 1, that does something in Hall Light that allows you to do things that you couldn't do on type real. Well, we don't have this in Isabelle, and we don't want it, and somehow Claude knows that when you're translating a thing, you turn real to the 1, simply translate it to real. And even more interesting, a general Euclidean space, that is R to the n, it translates to a polymorphic thing in a type class of Euclidean spaces, which is distinctly more general than real to the n. And again, it does that without being told to. And the proofs that you get really are idiomatic, and they are actually readable. The main my main criticism of its proofs is they're longer and more complicated than necessary. So they are very fine-grained. Another funny thing, you will often get a symmetry. Let's say you know, for example, either x less than y or y less than x. Then the theorem follows with 500 lines, which is duplicated with another 500 lines for the opposite case. And it'll do it. Seemingly, it won't even notice, or just says, right, my job is to do this thing. Bit like the Sorcerer's Apprentice. I think we're all going to have to study the Sorcerer's Apprentice if we work in this field. But anyway, I then go to my prompt box and say, the case x less than y and the case y less than x are symmetric, and those two proofs are basically the same. And it will say, oh, yes, they are. And then it will automatically extract out. So it will find out what things does the X less than Y case actually depend on, pull them out, give you a lemma, and then prove both cases with one line. And it will do that. All you have to do is tell it to do that. Maybe if the prompt were more elaborate and said, look out for that, then it would do that. But then maybe that would slow things down. So another thing I tried, this was in fact from Lean. Yes, the optional stopping theorem about things called martingales. All I know about martingales is that something to do with probability. So as usual, I'm totally out of my depth. This example had been done in Lean. I guess it was in MathLib, and there were two other MathLib entries that it depended on, so I had to port all of that. This was really easy, actually. For some reason, I don't quite know why. Maybe it's very well-known material, or it may simply be there's something about Lean. The proofs in Lean tend to be very short, and Lean, although it's not quite a structured language in the Isabelle sense, but you do have these have declaration where you can list the thing you're trying to prove next, and that also helps. So I was able to produce an Isabelle proof of the optional stopping theorem. I looked at it, it looked nice, but as I understand nothing about martingales, I'm actually unable to tell you whether this was correctly ported or not. Now, if there are any martingale experts out there, I will certainly accept volunteers. And this again is an issue, and I corrected the spelling on that last word, and I don't know why the correction didn't stick, and that really annoys me. Anyway, if anyone wants to volunteer to check this, please get in touch. Oh, and what does the source material look like? This is just the optional stopping theorem itself, not the two extra MathLib entries. This is the first half of it. Looking at this, I'm not going to call this super legible, but at least there is the theorem statement at the top. Then there is a have line. The other half. I bet the comments actually help the language model a lot. It really reads the comments. I'm sorry, I can't read this at all, but I think somewhere there is something that Claude was able to read because it was able to port this without any help whatever. Okay, now as for this one, the asterisks means I wasn't able to finish it. I was trying. I knew what the date of this talk was, but I'm afraid I didn't quite manage to do it. The main problem being that every time I thought I was almost there, there was another 500 lines of Hall light, really truly horrible Hall light proofs that had to be somehow formalized. And as before, Claude struggles with them. It is good in some cases, and in other cases, it needs to really be led by the hand. Anyway, the isoparametric theorem states that if you have a closed curve in a plane with a particular perimeter, if you want to choose one that encloses the largest area on the plane, you should choose a circle. So the main thing we had to formalize for this was a theory of bounded variation. Apparently, well, according again to Claude itself, this corresponds to an estimated 12,000 lines of Hall light. So a huge amount of stuff to try to port in a couple of weeks. As I said, I did not get to the end, but I got a long way. How I was doing this, and it is still a matter of figuring out how we use these tools. So again, I was not doing it the way Josef Urban did, that is, shoving material at Claude and walking away and kind of doing a pub crawl for the next 10 hours. That is not how I do it. Rather, I'm sitting there. I put in a prompt of some sort, telling it the next thing to prove. keeping an eye on it, and you can check your mail and things because it is quite slow. But you go back, sometimes you see that it seems to be on a wild goose chase. The proof looks nothing like what the proof should be, or maybe sometimes it even complains like it talks to itself. There is a little monitor window and it can see it saying things like, I seem to be going in circles. And then you can put it out of its misery by clicking the cancel button and seeing if you can give a different prompt. As mentioned, you can do part of your proof in Hull Light to see what it should be proving next, and then you can say, well, according to Hull Light, proving this fact would be really helpful. That can help. But also, there's a funny thing. Sometimes you can see where it's in the middle of a failed attempt. So you've got your Isabelle session just as if a human being were typing in. They typed in something and it's clearly wrong. It's like it's got error messages or it's looping. And you can even go in there. Now, as I hope most people know, Isabelle has a powerful automatic tool called Sledgehammer, which you can invoke simply by clicking somewhere and then clicking a button. That's all you have to do. If Sledgehammer then comes back with the proof, another click inserts the proof. And I have been doing that even while Claude is working. I would just kind of shove in and help it along by proving things along the way with Sledgehammer. Now, you might say maybe it should be using Sledgehammer itself, and maybe it should be, and maybe it will be, in the near future. But for myself, I want to keep an eye on it anyway, and then when I see it's been stuck, I can help it in that way. And often it is nearly there, so it has a proof that has failed, and yet I can see it's somehow looks quite close to what it should be, and that in those cases, Sledgehammer will do the job quite easily. And as I mentioned before, you can give it tips on how to refactor a proof it has found, and often that is successful. So what do I conclude from all this? Lean seems easy to port, possibly because proofs in Lean tend to be short. You don't get these 400-line wonders like you get in Hull Light, and Lean has more structure by far than, well, I was about to say more structure than a Hull Light proof. Now, John Harrison would disagree with me. They are, in fact, fully hierarchical, but this hierarchy is really only of use to a computer and not to an LLM type of computer either. It's interesting that language models are much happier to be given LaTeX than to be given a PDF. Okay. So now what? We can auto-formalize. Our problem is by no means solved. We are only getting started. And I want to remind people of the 1950s. What was Fortran? Fortran was a way of getting a computer to write its own code. Does that sound familiar? So now we think, is the output of a language model analogous to object code? Certainly, I see a lot of people inclining to this point of view, an idea that you should start with, let's say, an informal specification, let your language model formalize that to a formal specification, and then prove the specification, and then you can say, right, the computer has formalized it all and everything is good. I don't think so. I don't think that's a good idea. So, as I said, in the 1950s, we really thought of compilers as writing code for us. And this assembly language code that came out of compilers, well, I can't vouch for the 1950s because I was a baby then, but certainly when I was using compilers, I have never known anyone to say, look at all this lovely assembly language that the compiler gave us. Let's go and put in some comments and tune it here and there. No one does that. You run the code. That's what it's for. This machine language code is simply to be run. So, are we going to do AI in the same way? Are we just going to trust them? Don't we want a bit more? So, here are some responses. You see, people are a little worried. There's this classic. This was only a couple of weeks ago. Patrick Massot said this. I think thoroughly bomb this area to turn it into a giant radioactive wasteland feels really topical at the moment. Right. You know, Hulk mad. So what are we going to do? Well, what I'd like to say is that proofs are not compiled code. For one thing, if you are writing code in a programming language, it's precise. Now, you can quibble with this. There are ambiguities in programming languages, but these would be regarded as trouble spots of the language, which we hope over time to have completely unambiguous and rigorous programming languages. That is the ideal. Whereas mathematical texts are inherently informal, and very few people think that we should completely get rid of informal mathematical language. Also, the outputs are very different. So the compiled code that you get from a compiler is completely unreadable. There is no concession of any kind. There are indeed some compilers, or at least there were when I was playing with this sort of thing, that could deliver something that looked like a real assembly language code. But they were certainly no good at writing code that looked in any way like a human had written it. So don't expect labels to have intuitive names, for example, or routines to have intuitive names. Compilers are not good at thinking up names for things. But we don't want our formal proofs to be unreadable. At least I hope we don't. It's true that most of them are, but they don't have to be unreadable. Another issue that has been pointed out by a number of people is that the LLM might exploit the soundness bugs in a theorem prover. It's interesting. Now, of course, LLMs are very deceiving in how they respond to you. Certainly, I have never seen Claude when I have interacted with it, and it does give you all kinds of explanations. And it has never said, let me see if I can find a kernel bug that will prove this for us easily. It at least pretends to be doing it the right way. But if it finds that a proof goes through, it's quite happy with that fact. And it said, right, proved. And the idea or the concern that this proof should not have gone through, that that statement doesn't actually look true and that we should be worried, I don't think LLMs do worry. So we have got, we cannot count on an LLM to discover for itself that there are errors in our approach or in the prover itself. But also, if you're just going to trust the output of the LLM, say, right, the proof checker checked it, so it's fine, then you're just getting one bit of information from your proof. That is only it's okay. And people should not, in this day and age, simply be trusting computers blindly. Right. So we need to look at our proofs. Again, I'm trying to give the reason why I have been preferring this interactive approach that I've been talking about, as opposed to the batch approach of feeding a whole textbook in all at once. We should be keeping an eye on our proofs. We should watch them come out. We should make sure they're legible. So here is some automatically generated code that came out in the middle of this isoparametric theorem that I did not fully succeed in proving. I nevertheless proved a lot of stuff along the way, and this code you're looking at was generated completely by machine. I haven't tweaked this a bit as far as I know. So the indentation, the names of things, the name of the theorem, the names of the little lemma tags inside the theorem, all the variable names inside the theorem were all chosen by Claude. Claude thought that the vector variation should be called V and that the independent variable should be called T. Claude decided to prove that it was continuous. Okay, can people see the cursor? So there's the proof. You can see the things being proved. So here we're proving that this V, which we defined up there, is continuous on 0, 1. There is the proof. You can see that we are assuming a variable which it is called C in this interval 0, 1. It is proving that this fact here, it proves that fact, and finally it proves the following fact, which implies the conclusion. Oops. So you can read that. Equally up above, you can, sorry, I keep touching it. You can see that we're showing that G has bounded variation on 0, 1. We're showing it's continuous, and further down, we're showing that this function V is monotonic. So this is a readable proof. This is what I think we should be going for, which is why, of course, you should be using Isabelle. Yes, so as I say, we have in Isabelle the best of automath, the best of the whole system. It has the structured language very much inspired by the Mizar system. It has type classes from Haskell. We have structured proofs, which even the previous example I showed you a little bit of nesting, if I can go back a moment. So in this proof that V is continuous, we have a nested structured proof there. And of course, that allows us to have quite long proofs, hundreds of lines if we like. Also down here, we have another nested structured proof. So you can nest things as deeply as you like, and you can still see exactly what you're doing. So like if you're wondering about this line here, why am I showing that G has bounded variation on this interval here? Well, you see this Y came from right above, and you can see exactly what we're trying to prove at this particular moment. So, and I would argue, proofs should be legible, and this is still code. It is not, I can't argue that it's legible to everyone, but it is certainly a lot more legible than any alternatives that I am aware of. Of course, we also have the best automation out there, I'm pretty sure. And in particular, I find that Sledgehammer, which is our big automatic tool, is very good at both fixing and simplifying the output of Claude. I'm sorry, Claude, to call your output slop, but often Claude will prove a thing in a much more elaborate way than is necessary. And when you see a thing that looks like it's too fine-grained, you just point your mouse at the top, click on the sledgehammer button, wait a few seconds, and often you will get a single line that will replace like 5 or 10. And that is a way of making your proof look nicer, and also to make it, again, more your own proof rather than just Claude's proof. And of course, Isabelle has no dependent types. So I was actually told that if you want to play this game and you're not using lean, you have to explain yourself. So I'm explaining myself. Why don't we need dependent types? And I was asking Claude about this too. So Claude told me that people complain about things like 4 GB proof object. I had no idea proof objects could get so big. And if this is in fact a lie, Claude is the liar. I am not a liar. Claude told me this. Claude told me this. Universe polymorphism, I'm sure it has its uses, but it also apparently is a big pain point for people. I did not need Claude to tell me this, because this is why I left the type theory world 40 years ago, when intentionality was brought in. That, from my mind, was the end of dependent types even functioning as dependent types. It is a fact that dependent types are discouraged both by Lean's MathLib and in ROC, in both SS Reflect and the mathematical components. All of them discourage the use of dependent types except in the simplest cases. So no, we don't need dependent types. Now, actually, I think I need to give an explanation that is a bit more theoretical for the sake of mathematicians. A lot of people who really should know better, it seems, do not. So I think, and of course, I can't blame mathematicians for not being familiar with set theory. It's a kind of thing which is, frankly, for their point of view, an irrelevant pain in the posterior. But let me just say, I think it is well known, in fact, that when you have your universe polymorphism, basically you're working in a thing called Parsi-Grothendieck set theory. I won't say much in detail about this, but let's just have a little tiny thing to say that if you are doing mathematics, almost any mathematics apart from literally doing set theory itself, you are normally living in the tiniest little corner of set theory. In fact, a corner which is equivalent to simple type theory, which is a type theory normally supported by Isabelle. Now, of course, in Isabelle, there are things called axioms, which you can put in if you do want ZF. Yes, you can put in the ZF axioms, and indeed there is a prepackaged library of ZF for those very few people who need it. So I've done this in a few examples of my own. One of them was very much concerned with set theoretic ordinals, and the other had to do with the continuum hypothesis. So I needed to deal with cardinal numbers, but I also needed complex analysis. And it really was quite cool that you could combine complex analysis and something like cardinals and the continuum hypothesis in one world without any particular fuss. You would also need some kind of axioms, maybe just ZF, if you're doing something crazy like the surreal numbers, which the surreal numbers are not defined in the way of normal mathematical object, but they're basically conjured out of nothing. And for that, you do need some real power there. Now, let me just draw a little picture. So this is the universe of set. So this is the ZF universe. The shaded bit at the bottom is the Zermelo universe. So it is the tiny corner I was talking about. Now, in fact, at the very, very bottom, that is to say here, you've got the hereditarily finite sets. These sets are so simple that you could literally draw any of them on a piece of paper. So they are completely finite all the way down. So they're trivial. Well, there's some quite big ones, but they're all fully finite. So of course there's a limit to what you can do with that. And then when you reach the first dotted lines here, you have the union of all of those, and you suddenly have the infinite set, which is all of those things. And then as you go up, you start to get more higher and higher infinities and more complex sets of these things. So most of mathematics lives here, and I would include in that almost certainly a proof of Fermat's last theorem probably lives there. Now, I heard that the reverse mathematics has been applied here, and they've used reverse mathematics to suggest this. Now, I'm not an expert on reverse mathematics, and I'm not trying to diss it either, but I would argue that I see reverse mathematics as kind of like showing that you could build a starship out of stone tools. And it's a very interesting fact that you could build a starship out of stone tools, but no one wants to build a starship out of stone tools. So for me to say, yes, you could prove Fermat's last theorem here, but you would probably want to do literally anything else in the world, including, I don't know, swallowing a big bag of nails. Um, that's not a good advertisement. But I would think very likely you can prove Fermat's last theorem in this world without in any way suffering any more than you would suffering to go through this gigantic proof anyway. Because you see, most mathematics, people are making mathematical structures. Let's say they start with a group, you've got a carrier set, you've got a couple of operations, then you add a couple of components, then maybe you put in an indexed map of these things and combine that with some other things. And if you keep doing this, you arrive at things like schemes. So someone actually told me he thought, and this was someone who should have known better, that to do Grothendieck schemes, you surely need an inaccessible cardinal. But this doesn't make any sense because all you're doing, I have been through the whole construction of schemes, not that I understood it, but I could see that it is simply adding components, adding maps, attaching constraints, very complicated constraints, but imposing constraints does not even push you up one level of this hierarchy, and you've got infinitely many levels here. Every time you do another layer of maps from some index set to these weird structures, whatever they are, you go up another couple of levels, just a couple. And you can do this infinitely often, and you are still living here. So it is really quite hard to go above this shaded bit. Now, what is above the shaded bit? Well, there's some cool things. I wonder how many people know that the Aleph operator, you know, the enumeration of the cardinals, of the infinite cardinals, the Aleph operator has fixed points, and not just one fixed point. There is a proper class of fixed points of the Aleph operator. Now, you could argue that these are seriously big cardinals, but if you're a set theorist, you say, no, they're not big at all. They're trivially the proof of these fixed points of the Aleph operator is very elementary. So no, these are not what anyone means by a large cardinal. And if you go further up, God, there's all kinds of crazy stuff, and you're still in the ZF universe. So now, what is Tarski-Grothendieck? That means I want this multiplied by itself, a proper class of these. You know, this is nuts. So just to say, the reason inaccessible cardinals are called inaccessible is precisely because you cannot, using any number of combinations of all of the set theoretic principles, you cannot reach them. You have to postulate them. So it is completely impossible that the craziest list of definitions you could come up with could give you an inaccessible cardinal. Then if you equip yourself with a proper class of them, as it says there, it's like pushing about a wheelbarrow loaded with trillion-dollar coins. So it's very heavyweight. And then if you want to spend one, no one can actually accept them because they don't want to handle the change. And this is why dependent type formalisms they're a burden with this thing. It makes automation more difficult. It also can be confusing to users who can barely grasp what some of this stuff even means. And I'm not the first person to say this. This paper is 30 years old. Anyway, enough about dependent types. I would like to go back to the idea of AI as an interactive assistant. There's just the experiments I've been doing in the last few weeks have shown some things it can do. As I've said, I may have mentioned most of these already, so I'm almost getting to conclusions now. It translates from the languages of other proof assistants. It translates from ordinary mathematical text. It has a lot of general knowledge. Sometimes you give it a formula and it says, oh, you want to prove the such and such theorem. In fact, I gave Claude that diagram that I showed you a while back, a simpler version of it, and it said, oh, yes, that's a universe of sets. You know what? It's amazing. I can see why some people think these things are sentient. No, they are not sentient. It says, well, actually, the formula you've written is too complicated. Why don't you simplify it? Or it says, I don't think the thing you're trying to prove is even true. And, you know, it's not a human, it's not sentient, but nevertheless, it gives you the illusion of a really very competent assistant. It can help. And from my point of view, the main criticism now is that you have to wait so long for it to reply. It may be that in the future, language models will become faster at dealing with these. I mean, we're asking it to do really difficult things, so we have to give it some credit. Now, I want to give you some specific examples. This, again, is from my attempted proof of the isoperimetric theorem. What have we got here? If you can see, it has formalized the statement. It is formalized. It's done part of the proof. It has not yet finished the proof. Now, I assume it will finish the proof eventually, but at the moment, it's given us what it's got at the moment. It's actually very interesting and very useful that it can give us the skeleton of a proof that has not yet been proved. And in fact, in other applications where I knew something was difficult, I would ask it to list the milestones on the route to the conclusion and simply state them and then prove that those milestones did indeed imply the conclusion. So that way you can interactively produce a proof skeleton which you can then complete. And that, again, is why really you need a proof language which has nested structures as deeply as you want to go. So here we have a very simple proof structure which has just got, you know, you can see it is obtained an R greater than 0, satisfying some other property. And we then obtain some real number A with another property, and we have done all these things, and we have found this tag division has to do with integration. And then we finally, oops, I've moved on to my build, but it doesn't matter. We now see that the next thing we're going to have to do is the main conclusion itself from all the stuff we've done already. And this is Claude. Claude has told me all this stuff here. I wanted you to see it. It has explained it in plain English. You see, the proof contains P as a tag division of minus A to A, etc. I haven't quite read this. I think this is the steps of what it has done already. So this is not in particular, so sometimes it will give you a plan of what it needs to do next, but I don't think that's what we have here. This is a plan of what it's actually done. It's very nice that it can write an explanation for you. And of course, you can also ask Isabelle Assistant, remember this tool set we were started with, you can ask it to explain some Isabelle code and it can give you something like this. Here's another example from some kind of horrible proof of something to do with bounded variation or something. Now, again, this is all automatically generated code. You can see it's nicely structured. Now, this name shrink, I didn't come up with shrink as a variable name. It did. So there's some kind of telescoping intervals process going on here. Claude somehow recognized that was going on and decided that shrink was a reasonable name, which it is. You can also see in here some reasonable just identifier names. Why we call it K rather than X3492. And here from D, we've gone to D prime and so on and so forth. So again, a very intuitive looking proof. And again, a nice readable summary. And now it's telling us that it has managed to prove the theorem. So the last sorry has been proved. It's talking about the shrunken sum sequence sigma. And again, it invented all this language. I didn't suggest any of this. And all it had as a source was Hall-Light code. And Hall-Light, because it does not include any intermediate formulas frequently, it was not the source of these identifiers. It somehow did it of its own knowledge of mathematics. So again, we have a very nice explanation of the generated code, which I think is essential if you want to take ownership of this code. Other things we can do, you can ask why I can't do a certain thing. It might give an explanation. You can ask it if particular theorem is available. I even asked Claude to read the Hall-Light and explain what a certain thing in Hall-Light does, and ask it if there's something analogous in Isabelle. And it could say, oh, yeah, there is. It's called algebra. It does the same thing. And this, again, is like having an amazingly competent assistant by your side. And as I mentioned earlier, when I can see it's almost proved a thing and it's somehow stuck, I just go in myself while it's running and complete some proofs using Sledgehammer and help it along. So where do things stand? I don't want to make predictions that the field is moving so rapidly, it's insane. But it is clear that we can continue as we were doing, working interactively, but faster. If we get proofs done for us, they are messy proofs, and we should make them our own proofs. We should make them readable, and we should make them proofs that we understand and can believe, and we can use Sledgehammer for this. You can use many things as the raw material. Now, I'm not trying to be against Hall-Light. There's tons of stuff in Hall-Light, but it is my personal experience that Claude really struggles with Hall-Light as a source, where it's much happier if you give it something like LaTeX or Lean. And that's my conclusion. Let's just take the time to make real proofs that people don't have to take on trust, that people can actually look at, learn from, because that's what proofs are for. And by the way, I want to acknowledge my chums who are at Amazon who released this for us. That is Hanno and Dominic. And that's it.
Thank you very much.
Okay.
Very enjoyable talk with first-hand experience. There are a couple of questions in the chat. I will go over, ignore those ones that are Isabelle insiders about certain syntax notations like cartouche instead of syntax quotes, string quotes. But an interesting one, you emphasized a couple of times that it's important that the proofs and the output of the LLMs are readable. And yes, we had actually that discussion already in the last talk. And there is a similar comment here. Where was it? That we need a kind of an accountability and account for what it means that a proof is readable. Maybe can you give us some insights what for you means that this is a machine checkable but human readable proof?
Well, first, let me apologize for the repetition, but I had my grandchildren here, and I was really quite tied up in the previous hour, and they were just leaving, so I'm afraid I missed the previous talk. For myself, I mean, we have always it has been, I guess, since Macarius Wenzel invented the Isar language some 15 years ago, based very much on the Mizar language. We wanted readability for ourselves to make our proofs easier for us to maintain. And I guess, it has been a priority where I know it's not a priority for everyone. I'm not sure I quite answered your question, though.
Yes, a more the Isar language, so the specific syntax of Isabelle, for those that don't know, Isabelle has been already designed with being readable, but it's still, the colleague that is asking the question, I think, is a philosopher. Still, it looks maybe not that natural and easy to read if you're more used to, let's say, traditional textbook proofs. So I guess that's more a call for action, that we also need a common understanding what readability in terms of proofs means. I have here two questions about your actual experience with using Claude or AI for doing formalization. The first one is, what is if Claude or any other AI model tells you that something is not in the library if you're doing a lookup? How can you trust that? The person asking seems to have similar problems with querying the mathlib and getting the answer from Claude that things are not formalized that were actually already formalized.
Well, this is the problem of trusting language models. Yeah, it's better than nothing, but yeah, the great thing about theorem proving as an application is at least you can check that the proof is valid and know that there it is definitely telling the truth. But of course, in general, we can't trust language models. I wanted to get back to the previous point because I hadn't understood it. So in the case of readability, clearly an Isabelle proof is still computer code, and anyone who looks at it will see computer code. And the readability can only be relative to the alternatives. And you say, if this is at least more readable than that or the other. If one is wanting to push more in the direction of naturalness, there is an approach. There's a thing called an approach, which is a much more natural language based, where you really see what looks like ordinary mathematical text, which is then translated to Isabelle and actually interpreted formally. I'm not sure how far that goes in this sort of material yet. It needs to be developed further to be able to do these more advanced proofs. But certainly there is work on making really, really readable proofs, and there, I think you would worry in the opposite way, that is this really formal and what is happening formally underneath this beautiful layer.
Yeah, thanks. Yeah, for the people that don't know Naproche, I can encourage you to have a look at it. It really reads like natural language. I have one question. Did you experience any difference between suggestions for material that is in the AFP versus what is in the standard distribution of Isabelle when doing formalizations?
I don't think so. And what is weird is, as you say, yes, we can't trust language models, but even out of the box, they know a lot. So I remember asking DeepSeek, remember DeepSeek, something about the contents of the Isabelle libraries that I actually didn't know, and it knew. And I like, why would DeepSeek know that there was something about, I don't know, improper integrals and know where it is? And ChatGPT, even they are often right now, as it was said earlier, they're often wrong. But anyway, yeah, it doesn't really matter to us whether it's in the AFP or in the distribution, because either way we can use it, right?
Yes, correct. Another question I got is, do you have any estimates how the cost of your formalization works? I assume Kevin is asking it, and he had statistics about how much dollars his work did cost. So I guess he wants to compare it with that, essentially your cloud bills.
I don't know. I mean, I was getting the CPU time from through Amazon, so I wasn't paying for it. But I know that so Joseph Urban mentioned the cost of $150 for something. I believe it was simply the cost of feeding the topology textbook to Isabelle. And $150 actually sounds like very little to formalize an entire book. It's certainly a lot less than it would cost you to pay a human being to do that.
Yeah, that's true. Any questions locally? There's one question in the chat, but I think that's more one for the panel. So maybe we make a short break that also the panelists get a break. We can rearrange the system and we reconvene in 10 minutes. And the one question that I didn't pose, I think that is a good start for the panel. Then thank you again for a very enjoyable talk.
Thank you.